Bismillahirrahmanirrahim. In this video, we are going to continue with where we left from the last one. We discussed the basic concept about the Markov models, and in this video we are going to look at two of the algorithms of Markov model, and we are going to solve some examples with that. Just to recall what we did the last time, we were discussing about this example where we have three jars and each jar has a number of colored balls, and the problem was that you had to pick a successive number of balls at random, and at random means that the jars are moving around. There's a probability given, the probability of choosing one jar after the other, and the ball is in the jars, and you can calculate the probability of selecting a specific color in a specific jar. And this was the simple Markov problem, and we said that the hidden Markov problem is that you are given the sequence of events and you are asked to find the most probable jars from which these colored balls were selected. So using this, let's move on and look at the three algorithms that are mainly used in hidden Markov model. So the first one is, if I am given a sequence, what is the probability of generating that sequence? So here the problem is that you are given a set of jars, and you can see here we have red, blue, blue, green and red, and the question being asked is what's the probability of generating this sequence. So it's irrespective of the jars. We know the probability of the jars, but the question is irrespective of the jars, what's the probability that the selected balls will be red, blue, blue, green and red. So we have to select this x equal to x1, x2. Now this x are the first x1 will be red, and the second x2 will be blue, and then so on, given lambda. And lambda, I told you last time, it's the model. It's the combination of the transition, this diagram or this transition matrix, the probability of selection and the initial probability pi. So it's a set of A, B and pi. And so that's the first problem. The second problem that we are going to see is that in this case we're not being asked what's the probability of selecting red, blue, blue, green. In fact, we are told that red, blue, blue and green have been selected. We are being asked the reverse question, from which jars were they selected. So you know the outcome. You are being asked the sequence of events that led to the selection of these colored balls. And in the third example, it is about it's like using HMM as a classifier, and just like you had in the neural network, you had to learn the weights of the links. In this case, you are being asked to, you're not given these probability of transitions, and you are being asked to learn these probabilities. So we have already done many examples about classification and training, so I'm not going to cover this the third algorithm in this course, but we are going to look at the first two problems. So the first problem is given like this. So given a model lambda, and lambda is A, B and pi. A is the transition probabilities, B is the probability of selection of each colored ball in each jar, and pi is the initial set of jars, the probability of the selecting the initial set of jar. So I can even write it over here. So this lambda here is a collection of A, B and pi. This is my model. So given this, so the set of maybe red, blue and green balls, I am being asked what's the probability of x given q and lambda. So from here, one way is that I can I can generate the tree. So maybe if the first, so if my pi here is given as 1, 0, 0, it means the first jar was the first jar. Then I can say, okay, this is jar 1. I can select the first red ball from, so I can select the first red ball here, and the second one can be from jar 1, or it could be from jar 2, or it could be from jar 3, and the next blue ball is again from jar 1, jar 2 and jar 3 and so on. So I can calculate all those probabilities, sum them and get the answer, which is this expanded equation. Now this is exhaustive enumeration because you are going to build an entire tree, and this is the time complexity of that. It's not a very feasible solution because it's going to be very expensive. However, we can select a smart solution because each selection is based just on the previous selection. So if we use dynamic programming technique and we use a lattice structure based computation, this can be made very, very efficient, which we will see in the next couple of slides. So let's look at this example to see how this works. So in this example, let's call this jar 1 and let's call this jar 2 and this as jar 3. So the question is, let's make a question maybe, what's the probability of selecting red and green and blue? What's probability of getting this sequence? So this is the first example or the first algorithm, the probability of observing a sequence. So pi is given and it is 1, 0, 0. So we know that initially it was the first jar. So it's a transport. If you write it, it is 1, 0, 0 like this. So the probability, we know that the first red is from the first jar. So the way we're going to calculate this is, we can say that, okay, let's see the probability of selecting the first red element or the first red ball, in fact. So this is going to be, we know the probability of being in the first jar is 1. So this is going to be 1 multiplied by the probability of selecting a red from the first jar is 0.6. So we are going to give this a value of 0.6, which is 1 into 0.6. And this probability of selecting the first red from the second jar, since the probability of the second jar is 0, so we have 0 multiplied by the probability of red in the second jar is 0.2. So this is going to give me 0. And similarly here we also have 0 multiplied by 0, which is 0. So this is the probability of the first red ball being selected. We know it's from the first jar, so only this probability is of interest to us. Next, the second jar, it could have come, when we are calculating the second red ball, we are assuming that the first one was red, but we don't know from which jar it was selected. So we are going to assume it could be from the first, from the second, or from the third. So we are going to look at all those probabilities. And we are going to first assume that the second red is being selected from the first jar, or from the second jar, or from the third jar. And for each case, we are going to assume it could have come from any of the jars in the previous iteration. So what's the probability that from the first jar I will remain in the first jar and then select a red? So this is going to be the probability of selecting a red in the first jar was already calculated at 0.6. So this is going to be 0.6 multiplied by the probability of remaining in the first jar, which is 0.5 multiplied by the probability of selecting a red, which is 0.6. So what this means is, I got the first red ball from the first jar, and then I again selected the first jar, and I again selected a red ball. So this is this probability, and since this is 0, otherwise we would have make a link over here and sum all of them, but since this is 0, so anything multiplied by a 0 is going to be 0. I'm not going to count the contributions coming from this box towards this one. So I'm going to leave it as 0.18. So that's the probability of selecting the second red ball in the first jar. What if the second red ball is selected in the second jar and not the first jar? So it's a red ball, but it's selected from the jar number 2, so J2. Now again, this means that this sequence could have come either from here, or from here. So if this came from here, we have something like this, and we have something like this, and we also have something like this. So anything multiplied by it doesn't matter. In fact, you can't go from jar 3 to jar 1 in this graph. So it's going to be multiplied by 0, and the probability of selecting a red in the second jar is 0.2. So multiplied by 0.2, and this is 0. And this is 0 multiplied by from jar 2, remaining in jar 2 is 0.6. So I'm going to write into 0.6 into 0.2. This is again 0. But this one is 0.6 multiplied by the probability of going from jar 1 to jar 2. The probability of going from jar 1 to jar 2 is 0.4. So multiplied by 0.4, and the probability of selecting a red once we are in jar 2, which is 0.2. So this is 0.2. So essentially it is 0.6 multiplied by 0.4 multiplied by 0.2, which is 0.048. And what if we selected the second red ball from the third jar? This could have been either we came from this, let me erase this and try again. Okay, so if I have come from the first jar, this will be 0.6 multiplied by the probability of moving from the first jar to the third jar. So the probability of moving from the first jar to the third jar, which is 0.1. So multiplied by 0.1 multiplied by the probability of selecting a red in the third jar, which is 0. So multiplied by 0, and this gives, because there is a multiplication by 0, this gives 0. And then we move on to the next case. So now we have selected the first two colored balls as red. Now the third ball has to be green. If I am coming from here, this will be 0.18 multiplied by from first jar, remaining in the first jar, so multiplied by 0.5, and multiplied by green is 0.2. So multiplied by 0.2, and this is 0.018. Similarly, for the green ball to be in the second jar, I need to compute this, and I need to compute this. This is not necessary because there is no way I can move from the third jar to the second jar. So it's just going to clutter the whole thing. So 0.18 multiplied by, so what we have here is from the first jar to the second jar, which is 0.4. So multiplied by 0.4, and the probability of selecting a green, which is multiplied by 0.5. So it is RGB. So red, green, and blue. Green is 0.5. And so we have this, but we're not going to put it here. Let's see what we have from here. What's the probability of going from the second jar to the second jar and selecting green? So probability of remaining in the second jar is multiplied by 0.6 and multiplied by the probability of selecting a green, which is 0.5. So whatever answer I get here plus whatever answer I get here. And why plus? Because to be in the second jar and select a green, I could have come either from the first jar or remained in the second jar. there's no way I am coming from the third jar because there's no link. So it's either I am coming from the first jar or I am remaining in the second jar. And in probability, whenever you have an or, you plus. So it is 0.18 multiplied 0.4 multiplied 0.5 plus 0.048 multiplied by 0.6 multiplied by 0.5, and this is going to give me 0.0504. And for this case I could have come from here or from here or from here. So this is 0.18 and multiplied by from 1 to 3 it's 0.1. So multiplied by 0.1 multiplied by the chance of selecting a green, which is 0.3. So multiplied by 0.3, and this would be 0.048 multiplied by from 2 to 3 is 0.4 and multiplied by 0.3. So if you do this multiplication and this multiplication and add them together, you are going to get 0.0111 and finally for the blue we have either we could have come from here. I'm not calculating these ones because there is no way you can go back to the first jar. So it's just going to clutter it, otherwise everything will be multiplied by 0 and it's no use. So this will be multiplied by the probability of remaining in the first jar is 0.5 and selecting a blue is 0.2. So this is going to give me an answer of 0.0018, and the probability of ending up here is going to be either I'm coming from here or I'm coming from here, and this is 0.018 multiplied by 0.4 and multiplied by 0.3, and this is going to be multiplied by 0.6 multiplied by 0.3, and the answer here is 0.01123. And finally for the last one, I could have come from here, I could have come from here, or I could have come from here, and this calculation is this multiplied by 0.1 multiplied by 0.7, and from here it would be multiplied by 0.4 and multiplied by 0.7. And there is no self loop here, so I'm going to ignore this. So it's the same as multiplying by 0, and this is going to give me 0.01537. So what this tells me is that the last blue, the probability that the last blue will be selected from the first jar is this, from the second jar is this, from the third jar is this. However, this probability is not just the probability of selecting blue in the first jar, because that probability is 0.2. This probability means the probability of selecting R in the first jar and R in any of the other jars, and then G in any of the jars, and then finally blue in the first jar. This probability means selecting red from the first jar, then red from any of the other jars, green from any of the other jars, and blue in the second jar. And similarly, this is red on the first jar, red in any of the jars, green in any of the jars, and blue in the third jar. So the last blue would be either selected here or here or here, and this probability already includes all the possible variations. So this is where we are talking about that this is similar to a dynamic dynamic programming. So the values here already include because we multiplied this by this, and this in itself is multiplied using this, so it contains all the previous values. So finally we are going to say that the probability of selecting red, green or blue irrespective of the jars, this is equal to 0.0018 plus 0.01123 plus 0.01537. So this is the probability. This is the first problem in which we are trying to find the probability of a sequence. So I hope it's clear with this worked example. Now let's move on to the second question. And the second question was, I am given the output and I am being asked from which jars did we select this. This is called the most probable path decoding. So in this question or in this problem, the purpose is an analysis of the internal processing result and the best or most likely state sequence and the internal segmentation. This is called the Viterbi algorithm, and it again uses the dynamic programming technique. So like the previous one, we are given the model lambda, and this lambda is composed of A, B and pi. A is the state transitions, B is the probability of selecting a particular object in a particular state. For instance, probability of selecting blue in the first jar, probability of selecting green in the second jar, and pi is the probability of the initial state. So in this case, what we are trying to do is in the first problem, Q was irrelevant. We're trying to find the probability of X given lambda. In fact, it was X and Q. In this case, we are trying to find this probability such that this is an argmax, and argmax means you are going to use that value of Q that will maximize this argument. So you are trying to find the transitions that will result in the highest probability. So if I say that the sequence is red, green and blue, then you are going to calculate what possible sequence. If I use red from the first jar and red, if I use all of them from the first jar, I use first jar and second jar, and all those possible combinations, which one is going to give me the highest probability? That's what the question is asking. And the way to deal with that is so this is a mathematical representation of that. We're trying to find, so delta here is the path probability, and we are trying to find the maximum path. So, and this is the path node, and the node is the delta that resulted in that maximum value. So we are going to solve the problem just like we did previously. This is going to be the forward phase, and then we are going to backtrack and see from where we got these values. So if I take this example, instead of in this case, the value here was the sum of this multiplication and this multiplication, because it could have been either this or this. In the next problem, we are not saying either this or this, we are saying one of this. So when I'm saying one of this, it means I have to select the maximum value. And so we'll see in the next example, we have to go a forward phase, and then we have to backtrack and find the most probable value. So instead of going through all this mathematics, let's have an example. So this is the example that we have. Let's again try to find the same problem, RRGB. So this is going to be slightly more complicated, and let me put it this way. So let's the probability of the first red be here, and this requires some tricky manipulations. The first red here and the second red. and then we have the green, and then we have our blue. So I will also segment it like this. Great. So we move on with the same data that we have. So it is 1, 0, 0 pi. Our initial probability is that the first red is selected from the first jar. Let me label it again here. This is jar 1, this is jar number 2, and this is jar 3. So what's the probability that this came from the first jar? It is the probability of selecting the first jar, which is 1, multiplied by the probability of a red, which is 0.6. So this is going to give me a value. And what's the probability it could have come here? There is no chance, because the probability of selecting jar 2 is 0. So this is 0 multiplied by 0.6, and this is again 0 multiplied by 0.6. So I have this, and I take the max value, which is 0.6, and this is the max value. Then for this one, because it is J1, so this is going to be 0 multiplied by 0, 0, so I am going to have 0 here and 0 here. Similarly, these are all zeros. Why these are zeros? Because I am being told that the initial probability is the first jar, so only this will have a 1, everybody else will have a 0. There is no point doing these multiplications, they are all going to be zeros. Let's move on to the second R. Now, if I come from here, then the probability will be 0.6, which is this one, multiplied by, from jar 1 remaining in jar 1, which is 0.5, multiplied by selecting an R, which is 0.6, and this is equal to 0.18. The probability that I come from here, so these are all zeros. Even if I come from here, this is going to be 0 multiplied by, and I cannot move from the second jar, so these are all 0, and this is also 0. So this is the probable value. Here also, this is the most probable or the maximum value. In this case, I could have come from the first jar, remain in the second jar, or in fact, I can't come from the third jar, because there is no link from 3 to 2. So if I am coming from the first jar, this is going to be 0.6. This is the probability, multiplied by moving from the first jar to the second jar, which is 0.4. So multiplied by 0.4, and selecting a red from the second jar, which is 0.2. So multiplied by 0.2, and this value is 0.048, and anything else here is 0 and 0, and this is also 0, 0, 0, because there is no way. If I could have come from here to here, but that would be 0.6 multiplied by 0.1. So from jar 1 to jar 3, this is 0.1, and then selecting a red. So what's the probability of red? It is 0. So multiplied by 0, this gives me 0. This is 0, so it could have been 0 multiplied by 0.4 multiplied by 0. So this is 0 into 0.4 into 0. There is no point in all these calculations. So the idea here is that if I end up in this box, it means I have come from here, and this is the value. If I do end up in this box, it means I have come from here, and this is the maximum value. So because for each box here that I have drawn, we have 3 values, and it signifies the probability of coming either from the first jar, from the second jar, or from the third jar. So let's move on. Let's go to the green. Now this is where things will be getting more interesting. So if I came from the first jar, this would be 0.18, which is this probability, multiplied by remaining in the first jar, which is 0.5, multiplied by selecting a green, which is 0.2, and this is 0.018. And if I'm coming from the second jar, this is 0.048 multiplied by, there's no way I can move from the second jar to the first jar, so multiplied by 0, and similarly here this will be 0. So this will be 0 and this will be 0. So if what's the max between these three values? It is this is the max value. In this case, I can come from here, or from here. If let's try from the first one. So this is 0.18 multiplied by jar 1 to jar 2, which is 0.4, multiplied by a green in the second jar, which is 0.5. Right, so I have this, and the probability of coming from the second jar, this would be 0.048 multiplied by remaining in the second jar is 0.6, so this is 0.6 multiplied by 0.5. So this is going to be 0.036. Here we have 0.0144, and this is going to be 0 because I can't move from the third jar to the second jar. So between these three values, this is the maximum value. Next, in this case, we have 0.18. So the first jar multiplied by moving from the first directly to the third is 0.1, and selecting a green is 0.3. So this is 0.0054. And the second one option is 0.048. So this is assuming I am coming from the second jar multiplied by 0.4. This is an 8, and multiplied by 0.3. This is going to be 0.00576, and here it's 0. So this is going to be 0. So among these three values, the highest one is, so they have both double zeros. This is 54, this is 57. So it is the second value. Now we move to the last part, the blue one. So this is going to be 0.018 multiplied by remaining in the first jar is 0.5, and multiplied by selecting a blue is 0.2. So this is going to be 0.0018, and this is because there is no way I can move from any of the other jars to the first one, it's irrelevant calculating this. So this is 0, and this is also 0. The max one here is this. Let's move to the second jar. So here we have 0.018 multiplied by 0.4, and multiplied by blue in the second jar is 0.3. So 0.3, and this is 0.00216. We have 0.036, this value multiplied by, so this is jar 2, remaining in jar 2 0.6 and 0.3. This is 0.00648, and finally from the third, there is no way I can move, so anything will be multiplied by 0. So this is simply 0. So in this I have, but doesn't matter, it could be anyone. So for the third case, let's look at this 0.18 multiplied by, so this is, sorry, 0.018 multiplied by 0.1 multiplied by, so a blue here is 0.7, so multiplied by 0.7, this is 0.00126. If I come from the second jar, this is going to be 0.036 multiplied by 0.4 multiplied by 0.7. This is 0.01008, and from third one is, since there is no self loop here, so this is simply 0. So among these two, this value is higher. So once I am done with this, and here we have, I think there is an extra 0 here I'm missing. I think there's an extra 0 here. So I have this value as the max. So this is the forward path. Now let me just let me change the color of my pen. So now I have 3 values to look at. This is, if I am in this box, it means I am in jar 1, this is the maximum value I have. If I am in jar 2, this is the maximum. If I am in jar 3, this is the maximum. So I make a comparison. This is 0.0018, 0.00216, and point. So this has only 1 0. So this is the maximum value I have among 1, 2, and 3, among these 3 values. This is the maximum value here. How can I end up with this? This is from the first jar, this is from the second jar, this is from the third jar. It means that to be able to get this value, the previous one would have been from the second jar. It means that this value comes here. So I'm going to draw an arrow. So this is how I end up with this value. If I look here, this comes from the first jar. So I'm going to make an arrow here, and then this all comes from the first jar. So I'm going to make an arrow here. So what is the most probable path? The most probable path is, so if I look at this, I'm coming from here, then this, then this, and then this. So the most probable path, let's write it here. Most is, so this is J1. So J1 from where I got the first red, then J1 again from where I got another red, then J2 from where I got the green, and J3 from where I got the blue. So given that we have RRGB, it's most likely that we got it from the first jar, the second jar, and the third jar. So this is basically the answer. This is the most probable path that you're trying. So I hope with this calculation it's pretty clear. Since this is a video, if you don't understand it, the good thing is you can watch it again and watch it again, and it's not that difficult. It's a bit of calculations, but it's not that difficult to follow. You just need to see that you have to do all the calculations, and instead of taking the sum as in the previous case, you just have to maintain the max, and then in the last column, look at the max which is the highest, and then figure out where you came to from this value. So just backtrack, and you will end up with the most probable path. So in summary, what we studied here was the hidden Markov model, and it uses the first order Markov assumption on the state transition. It means that the current state is only dependent on the previous state, which is we can see here. So when we were calculating this, we only used this probability and not all the previous probability, because this probability already contains all the previous probabilities. It can be used as a classification algorithm too. We did not see that because we didn't do the third part. And there are 3 algorithms: model evaluation, we did that; most probable path decoding, we did that; model training, we skipped this part. And it's used in many areas, for instance for handwriting recognition. So using this transitions and the probability, if I am writing like this, so the software is guessing whether I'm going to write an a C, or I'm going to make a D. So it's at all points it is guessing what I'm going to do, and it may even offer suggestion. Similarly, if I write for instance probable, now it is going to see that this is the set of transitions. So this is the same as saying red, green, blue, and what is the next one. So once I write this, there is a good chance that it's going to tell me that this is probably the word I'm trying to write. So this is how the hidden Markov model is used in practice. It's used in handwriting recognition, it's used in speech recognition, in gesture recognition. So if I'm working in a video, you are trying to, at every time you're trying to predict what my next move will be. Either I'm going to start running, whether I'm going to turn left, I'm going to turn right, I'm going to sit down, or any other activity that I'm going to do. So this is a case where HMM comes in very handy. Finally, I have left a link to two very good toolboxes. One is for the well, you can use it in any way. This is specifically for speech recognition, and this is another link. So you have the models there. You can use it. You can use the APIs there, and then build your own HMM model and work from there. So that's it for this video. I hope you enjoyed it as much as I did. As I said in the very beginning of this video, this is my favorite algorithm, because it allows you to look at a problem from very different perspective using probability. So no other algorithm is going to be able to give me this prediction or tell me how I arrived at this RRGB. So this only happens in hidden Markov. There are other algorithms, we haven't studied it. Among the ones that we have studied, HMM is the only one that's capable of doing that. So I hope you enjoyed this video. Thank you very much for watching. As previously, if you have any questions, you can either ask in the comment section, you can ask on the MS Team webpage, or you can ask during the question hour session that we'll have later in this week.